to our presentation that helps you look beyond the datasheet. My name is Nick Dutton, I'm with Silicon Labs. Let's get started. When developers start a new design, they need to select the most appropriate components to meet their goal. Datasheets are a good place to start, and they do offer the specifications on key parameters. But the numbers must be assessed with open eyes, because even specifications that appear to be the same may be measured differently, may be optimistic, or even misleading. The numbers in a datasheet may not represent what the designers will always see once the component is implemented in a product. This is because the developer implementation may be different to that of the author's implementation. Also, consider the influence of software, a protocol stack, the services it offers, and the dynamic nature of it all greatly influence battery life. The only way a developer can truly understand how a component performs is through benchmarking, where the developer can control the test conditions and use it in a manner that best represents their product's use case. To illustrate this, we will look at some of the datasheet limitations when we're looking at published numbers in 4 802.15.4 and BLE devices available from different vendors, and how the similar numbers may actually impact your product performance and battery life. One of the easiest variables to demonstrate this phenomena is in memory size. Published numbers do not necessarily provide an accurate representation of usable flash or RAM in a wireless device. Different protocols by different vendors used on different platforms can consume significantly different amounts of memory. This could be due to different services offered by the stack, different levels of error handling in the stack, or the matureness and optimization factors between vendors. Indeed, vendors with more mature stacks may put portions of the stack in ROM, freeing up flash and RAM resource for the developer. Hardware cryptography can also influence current consumption numbers across the different vendors. By example, Vendor C has a dedicated security core optimized to perform elliptical curve operations in just over 5 milliseconds, whereas one of the other vendors takes close to 80 milliseconds to perform the same operation. This information is not in their datasheets, nor is it in any of their other published documentation. You may also believe that reading values such as the maximum transmit power would make for a straightforward comparison, but often such detail can be subject to caveats that are less obvious. Maximum transmitter output powers may require higher voltage levels, and the chip itself may not be able to run those voltages directly from its own DC to DC. It may be that the power amplifier needs to run from the system battery or from different voltage domains in the design. Under these conditions, the transmitter may actually use increased current consumption that is not accounted for in the current consumption figures of the datasheet. In this table, we can see that vendor D requires 3 volts to run up to an 8 dBm output power, whilst vendor C can run up to 14 dBm at only 1.8 volts. Active current figures could also be considered an easy variable to compare with, but they can still be deceiving as there are so many different options. By example, does the number represent the same test conditions across all vendors? Does it represent an application running from flash or RAM? Was the test done while running a prime or a while loop? It is also often that vendors will perform these tests at max CPU speeds, while other specs may be measured at lower speeds, and so the microamps per megahertz may be higher. Furthermore, do the measurements consider MIPS? Processing time may vary vendor to vendor, leading to an overall increase in current consumption. In radio specifications, measurements could be taken at the crystal speed, or could be taken at a multiplier. Sleep current tends to be one of the bigger offenders in variability amongst vendors. What does the sleep number actually represent in the datasheet? By example, how much RAM is retained during the sleep state? In reality, the application itself dictates what is the best sleep options you should be looking for. When choosing to use a system cache, sleep currents may be higher, But then if we opt to disable it, saving current during sleep, the reconfiguration events on wake-up may actually use more energy. This can also be a key factor in determining the overall current consumption of sleepy devices, and only taking the actual application into account provides a true sleep number. In SoC solutions that are made up of an MCU and a radio, it is often important to understand how the vendors list current consumption in their datasheets. Some vendors only list RF current consumption, choosing not to list the MCU component. Others may include it, but only accounting for it in an idle state. Benchmarking is therefore important to perform, as it helps demonstrate the current consumption in transmit and receive operations that also represent the application. Radio output power and sensitivity may also greatly affect the total current consumption by the system, and we'll look at this aspect shortly. Supply voltage itself may also affect current consumption. Datasheets may not be representing the same specifications at the same voltage. This may lead to deceiving current consumption comparisons. Current consumption needs to be evaluated at a fixed voltage. Developers also need to consider DC to DC efficiency and its operating range. By example, if a DC to DC cuts out at 2.5 volts, it will likely switch to a bypass mode, significantly increasing current consumption. Furthermore, as we discussed earlier, transmitter output power is often dependent on the voltage, so some solutions may not provide full output power capability if the voltage gets too low. As such, developers with designs that must have those higher output powers need to consider more variables than just the single datasheet specification labeled transmit power. So as we have established, datasheets offer a good initial introduction to a device, but it's important to delve beyond just the high-level numbers. What is the voltage that the numbers in the datasheet are based upon? Have the footnotes in the datasheet been considered? What peripherals or features are turned on or off during the sleep states? Is the CPU represented in the transmit and receive currents? Do any of the peripherals require other power domains to be available? Can full transmit power be achieved at the lower voltages? And what non-typical conditions will drive a higher current consumption or performance limitation? Wireless products call on developers to consider a number of additional variables: the transitions between active and sleep states, DC to DC voltage ranges, and efficiencies across those voltages. So developers need to consider scenarios and understand how those variables act upon each other, because looking at the basic specifications will not answer all the questions. What is the minimum voltage the DC to DC will need? What are the efficiencies it will provide at these lower voltages? When a developer asks themselves these questions, they may come to realize that when vendor A states a specification, they may also assume 100% efficiency on the DC to DC. This of course is not realistic, and higher currents will occur than those offered in the datasheet. Other RF factors can also affect the battery life. For example, vendor D requires 3 volts for an 8 dBm output power. This may be fine for mains powered devices that have regulated 3 or 3.3 volt power supplies, but in battery applications this is not useful. In addition, aspects such as channel rejection and blocking performance have significant impact also, but this data is not even included in the datasheet by some vendors. Let's take a close look at RF performance, given it is often overlooked when it comes to battery life. Product developers need to look at current consumption to maximize on battery life, but poor RF performance can significantly increase RF retries, which in turn greatly affects that goal. To compare vendors on a more level playing field, developers can look at both range and current consumption to determine the microamps per meter, but these figures are not provided in datasheets. To aid in these calculations, Silicon Labs offers a range calculator on its website. This will help you better understand the estimated range of any radio devices by simply entering the various data from that vendor's datasheet. When we benchmark the vendors A through D, the following results can be seen for BLE performance in the presence of a -30 dBm Wi-Fi blocker. This shows a significant difference in performance of about 20 to 25 dBm across the vendors. This also shows vendor A and D would require significantly stronger signals to receive in the presence of a strong Wi-Fi blocker. This in real life surfaces as less range and a greater number of retries being performed, which in turn affects the battery life of a product. So why does RF performance matter, especially in mesh networks such as those using Zigbee, Thread or Bluetooth mesh? In this example, we will look at a Zigbee or Thread network, but the concept also resembles that of other mesh networks. We can use this illustration to show how the radio performance can affect a network and the battery of an end device. This diagram shows coordinators and routers, all typically mains powered, and it also shows sleepy end devices which are battery powered. Let's remind ourselves how a message travels across nodes to get to the end destination. In this case, the message will travel across 3 mains-powered nodes and use 4 hops. Now, using the same network, but when using better performing radios, you can see that the communication can occur over further distances, reducing hops. By example, this animation shows the new route that the message has taken, reducing those hops to 3 and therefore the amount of traffic in the network. The additional route also offers another path for the message, providing a greater likelihood that the message will still make it to its destination if a node fails. And now by comparison, we see a battery-powered sleepy end node transmitting its message through a parent node, which in turn then forwards the message on until it reaches its final destination. But if the device loses its parent, or there is no parent in range, then the sleepy end device will not be able to successfully send its message, resulting in more transmissions and, in more severe cases, the orphaning of the sleepy end node. If a battery-powered sleepy end node, however, has better RF performance, it will find a path to another parent. The new parent forwards the message, demonstrating how that in some scenarios RF performance reduces both traffic and enables alternative routes for message delivery. In a design, there are many other aspects other than the numbers in the datasheet that can affect RF performance and battery life. Protocol stacks have a direct impact on both battery performance and the required amount of memory needed by the product developers. The protocol's timing and efficiency can directly affect battery life. These could be considered as independent from those of the hardware. By example, a chatty network protocol may result in transmit and receive being a bigger part of the overall current consumption, whereas a sleepy network may rely more on the sleep current being the bigger contributor. Furthermore, protocols with smaller payloads may have a higher cost in power per byte because more of the message is used for network information and security. As suggested earlier, datasheets may help narrow down the list, but benchmarking is really the only way to truly understand how a solution will perform. So given we know benchmarking is important, let's look at the concept a little closer. Looking at this illustration, we see a capture of the current consumption experienced by a Zigbee sensor. We can see that the device starts asleep, it then wakes, potentially due to a timer, it transmits its data to the parent, before transitioning to a receive state to look for an acknowledgement from the network. It finishes with some post-processing, and then returns to sleep. These captures allow a developer to create a battery calculator for their application. Developers can see how different transitions and specifications will affect their product's battery life. In this calculator, we input the numbers from 4 vendors, allowing the developer to see how different sleep, transmit, and receive currents affect total current consumption. When we look at the initial results, battery life will be comparable across all vendors. But vendor C offers a better link budget, and therefore a greater range and more robust links. If we were, however, to change the data pole interval to a larger number, in this case from 7 seconds to 300 seconds, you would see that the sleep current would have a greater impact on battery life. And then vendor B would offer a significant improvement. In this battery calculator, we focus only on the radio for simplicity, but we must remember a final product does need to take other activities into account, such as sensor readings and MCU. Another caveat of this simple calculator is that there is some lack of accounting for the current consumption used during the timing of transitional states of the device. In this new capture, we look at an example of a BLE advertisement. The device wakes up, performs 3 transmit and receive operations in a set time frame, and then goes back to sleep. While there are some timing dependencies that must follow the specification of the standard, others are more flexible. By example, time to wake up, time to process, time to go back to sleep, and what mode the device can be in between any radio activity. When we compare this to Zigbee, we can see that the transmit time for Bluetooth is much longer, and so the radio puts a larger burden on the battery life. However, Bluetooth sync time when making a connection is much lower than that of Zigbee. Therefore, it is a lower burden on the battery during that period in time. In this calculator, we look at a single vendor for a BLE slave device, and as we recall, BLE active mode, MCU active mode, transmit and receive are all the most dominating states for current consumption. Reviewing these numbers, we see that transmit consumes the larger percentage of the current in this application. This is because the developer intends to transmit at 10 dBm, a state that consumes nearly 3 times the current of receive. With this final diagram, we're going to help you understand why benchmarking is so important. This example shows a Bluetooth slave device wake to receive a packet. It then transitions to transmit, processes the data, and returns to sleep. When reviewing the datasheets, sleep currents between vendors are all comparable, but vendor E appears to have a lower transmit and receive current. The test, however, revealed that the timings for the transaction were substantially longer for vendor E, possibly due to the wake-up times or efficiency of the stack. The test also revealed that the transmit and receive current were actually higher than represented in the datasheets. The arrows illustrate where the datasheet suggested the value should have been, but the capture shows higher currents for both. Tests showed vendor E had the larger delta with the datasheet at 3 milliamps. Adding to the growing list of revelations, the test showed that vendor E took a very long time to return to sleep after the connection was complete. So when we summarize the benchmark test, we can see that the total current consumption for the event shows that vendor C is actually 50% lower than vendor E, even though on paper it appeared that vendor C was actually 30% higher. This demonstrates why benchmarking is so important to understand the total current consumption of any device. So at this point in the presentation, we can see that datasheets don't allow developers to easily create an apples-for-apples comparison. They can often be very optimistic or misleading. Key parameters can often be overlooked or difficult to find. Protocol stacks can greatly affect what is important to a sleepy device. Product developers need to consider their application, since active current and sleep current have long-term effects on the battery life. Different vendor implementations can also affect total current consumption. Radio performance will be affected by real-world and environmental issues and can lead to retries, shorter range, and even more bandwidth utilization. And finally, benchmarking is the only way to properly assess current consumption and estimated battery life. With this, we hope you gain some insight into what to look for in datasheets, and we hope you find our battery calculator useful. We look forward to meeting you again in one of our future presentations.